Good morning, people. I'll be right back, okay? Morning. All right, we've reached 20, so that means I'm going to start. Look at these glasses. Push them up, and here they go. Now, of course, I push them up and they stay up. All right, so I just push them up again, slide down. So, I've got a relatively quick lesson for you guys today. I'm probably going to let you out a little bit early from the Zoom room. Let's power through it. Let's do this. Let's do some physics. Physics Friday. I've been teaching physics for 10 years now, and I've never thought of the term Physics Friday. So what we're going to learn about first is something I like to call the sneaky form of Newton's second law. So if you you won't find, if you look up sneaky form of Newton's second law on Google, you won't find anything. This is just what I call it, okay? So basically, we're just going to rewrite Newton's second law in terms of momentum, okay? So if you recall, Newton's second law is net force equals mass times acceleration. So now what we're going to do is we're going to write acceleration. We're going to write the definition of acceleration. So if you remember, acceleration is the rate of change of velocity. So we have m times delta v over delta t. And what we can see is we have mass times velocity right here. Mass times velocity. Mass times velocity, well, jeepers, that's momentum. Right? Momentum is mass times velocity. So, but there's a delta in here. So it's change in momentum over change in time. So we would call that the rate of change of momentum. And so basically, the sneaky form of Newton's second law is this. The net force is equal to the rate of change of momentum of the object. Okay? I like this form of Newton's second law. It can be useful. Let's do an example to see how it can be useful. Okay? So let's imagine that we have a wall. So the wall is, there's a wall. And we have a ball The ball has a mass of 0.2 kilograms, and the ball is headed towards the wall with a speed of 20 meters per second. It hits the wall and it bounces back. It's not a perfectly elastic collision, so it bounces back with a little bit less speed, maybe 15 meters per second. Okay. Now you're watching this collision of the ball with the wall using a high-speed camera. So maybe you've seen this. I've seen it. There's various YouTube channels that basically their entire YouTube channel is just they have a high-speed camera and they do cool stuff with it. And so they have cameras that are so high speed that you can see a ball hit a wall and you can see the ball compress and then decompress and bounce back in the opposite direction. So you have one of those cameras. And so a high-speed camera shows that the time of contact with the wall is 0.005 seconds. Okay? So the only way, that's much too fast for you to be able to tell with your eyes, but if you have a high-speed camera, you could actually measure the time of contact. So let's suppose that you did that. What we would like to do is we would like to estimate the force the wall exerts on the ball. And so we're going to do that using the sneaky form of Newton's second law. So first of all, let's calculate the initial momentum. The initial momentum is mass times velocity. Okay? Mass, which is 0.02 or 0.2, times velocity, which is 20 meters per second to the right. So plus 20. So multiplying that out gives an initial momentum of 4 kilogram meters per second, plus 4. The final momentum is also mv. We have a mass of 0.2 and a velocity of 15 meters per second to the left. So we got to make sure we include that negative sign in there to indicate that it's going to the left. And so we have P final is 0.2 times negative 15, which is negative 3 kilogram meters per second. Based on this, we can calculate the change in momentum, because change in any quantity is final value minus initial value. Okay? So the final momentum was minus 3. The initial momentum was plus 4. Okay? So that gives us a change in momentum of negative 7 kilogram meters per second. All right? So now we go to the sneaky form of Newton's second law, which says that net force is rate of change of momentum. I know that the change in momentum was minus 7, and I know that the time of contact was 0.005 because of the high-speed camera. So we can do this. And that gives negative 1400 newtons is the force that the wall exerts on the ball. Now, why is that force negative? It's because we can see that the wall takes the velocity and reverses it and makes it a leftward velocity. So that means that it's a negative net force, okay? The other thing is, notice how the sneaky form of Newton's second law refers to the net force. So I'm kind of assuming that the wall is the only force on the ball at that particular instant, okay? Because the rate of change of momentum tells you the net force. So if there were other forces present, then, well, negative 1400 would be the sum of all of those forces. So I couldn't isolate just a single force. Okay? So anyways, the sneaky form of Newton's second law is useful. Now I want to talk about another thing, which is called impulse. So I'm going to be teaching you two different ways to calculate impulse. All right. The first way that I'm going to have you calculate it is for a constant force. All right. So if you have a constant force, the impulse, which is denoted by J, is equal to the size of the force times the time that that force acts for. So that is the definition of impulse for a constant force. Okay? Based on that, we can easily determine the units of impulse. So the units of impulse, well, impulse is a force multiplied by a time, so newtons times seconds. Newton seconds are the units of impulse. All right? So I just defined this. What I would like to do is sort of talk about why is it useful to define impulse. Why is it useful to define impulse? Well, to understand why it is useful, well, first of all, I'll give a couple of different reasons. One reason, impulse is used extensively in rocketry. Okay? Why is that? Well, if you think about a rocket will, when you turn it on, it basically keeps going until it runs out of fuel. So you have the time elapsed. The time elapsed would be the time for the rocket to run out of fuel. Okay? The force would be the force that the rocket exerts on the space probe or whatever it is. Okay? So one of the ways that you characterize a rocket engine is by the impulse that it provides. Okay? Force times time. You could have a weak rocket that fires for a really long amount of time, so a small force but a big time. Or you could have a strong rocket that has a huge force but only lasts for a short amount of time, and those two different rockets could have the same performance. Okay? So the impulse is kind of like describes the performance of a rocket engine. Okay? For this class, though, the reason that it is useful to define impulse is we basically go to the sneaky form of Newton's second law. And what if I multiply both sides by delta t, by the time elapsed? That would move delta t to the other side of the equation, so I have delta p equals net force times delta t. All right, but then if I compare this to the definition of impulse, I can see that that is the definition of impulse. All right, so the change in momentum is equal to the impulse. But we have to be careful here because individual forces can have impulses. You can talk about the impulse of the rocket engine. You could talk about the impulse due to the gravitational force. You could talk about the impulse due to friction. Those are impulses due to single forces. But the change in momentum is the impulse due to all of those forces combined because we have the net force right here. So the impulse, the net impulse is equal to the change in momentum of the object. So that is why it is useful to define impulse. The net impulse is equal to the change in momentum of the object. Okay. So let's do an example. Let's suppose a 3 kilogram object falls through Earth's atmosphere for 7 seconds. Calculate the impulse due to gravity. Okay, so calculate the impulse due to gravity. So the definition of impulse is force times the time elapsed. Now the force that we're talking about is the gravitational force. So that force is m times g. Okay. It is a 3 kilogram object traveling through Earth's atmosphere, so that means that g is 10, or approximately 10. And it's falling for 7 seconds, so the time elapsed is 7 seconds. So multiplying all that out, you can do that in your head. It's 210 Newton seconds is the impulse. All right. Notice how in this case we cannot set impulse equal to change in momentum because this is only the impulse due to one of the forces. Okay. But the net force on this object is probably going to be two forces because we said it's falling through Earth's atmosphere. So we also have a drag force. All right, so we couldn't calculate the change in momentum without also knowing the impulse due to the drag force. Okay, let's do another example. A 3 kilogram object, again with my 3 kilogram objects, moves left at 11 meters per second. A net force of size 40 newtons to the right acts for 2 seconds. What is the final velocity? Okay, so let's work through this. So let's calculate the initial momentum. The initial momentum is mv. Okay, so m, which is 3 times to the left at 11 meters per second, so negative 11. So that is an initial momentum of negative 33 kilogram meters per second. The final momentum, well, I'm trying to calculate the final velocity, so I don't know what the final velocity is. Okay, so for that reason, I'm just going to leave the final velocity as a variable and say 3v final. All right. The impulse is force times delta t. All right. So we have a 40 Newton force to the right, so that's a plus 40 force, and it acts for 2 seconds. So that means that the impulse is plus 80 Newton seconds. All right, now there's one key phrase that's going to allow us to solve this problem. It says that it is the net force. So this impulse is not just any impulse due to any random force. This is the net impulse. Okay? So because that is the net impulse, I can use the equation change in momentum is net impulse. Okay? The change in momentum is P final, which is 3V final, minus P initial, which is negative 33. So we have to be careful here because we have final minus initial, but the initial is negative, so we have a double negative here. Okay? Delta means final minus initial, and then we have an extra negative from that. So we have two negatives. Make sure you understand why we have two negatives. That equals 80. Two negatives makes a positive. Subtract 33 from both sides, we get 47. Divide both sides by 3, we get, 15.6. Alrighty. So, almost done here. What I would like to talk about next is, so I taught you how to calculate impulse for a constant force. What if you have a non-constant force? How do we calculate impulse due to a non-constant force? Well, if you have a non-constant force, then I have to tell you in what way is that force not constant. I can't just say the force is, oh my god, I can't just say the force is not constant. Figure it out. I have to tell you how exactly is the force not constant. And so one of the ways to do that would be to give you a force versus time graph. Okay? So maybe the force versus time graph looks like this. So this would be a force that increases as time goes on and then immediately drops to 0. It's an example. Okay, you could draw any graph you want. But if you have a force versus time graph, the area under the curve is the impulse due to that force. Okay? So the key thing here is the impulse equals area under a force time graph. All right? So that's an important factoid. let's turn this into an example, okay? So I'm going to actually make this a specific graph. So let's say that the force ramps up over the course of 5 seconds. And the peak value of the force is 100 newtons. And furthermore, let's suppose that this is the net force, so that this would be the net impulse, okay? So let's suppose that this force acts on a 4 kilogram object initially at rest. What is V final? I got woken up by helicopters this morning because there was a fire in kind of like directly north, like up in the hills north of Laverne. And the helicopter was going back and forth between the fire and Pudding Stone, picking up water. So it was, and my house is like directly along that path, and so it was just like this morning. Okay, so we're trying to figure out the final velocity. So P initial is 0. Why? Because it is initially at rest. Okay? It's initially at rest, and momentum is mass times velocity. So if your velocity is 0, your momentum is 0. The final momentum, well, it's a 4 kilogram object moving at a certain speed, v final, so 4 v final. We're leaving that as a variable. So that means that the change in momentum is final momentum minus initial momentum. So because we're subtracting 0, that doesn't do anything. We just get final momentum as 4 v final. Okay? Now let's calculate the net impulse. Net impulse is going to be the area under the force time graph. This is a triangle, so I have 1/2 times the base of the triangle, which is 5 seconds, times the height of the triangle, which is 100 newtons. All right, so I have 0.5 times 5 times 100. So that gives us 250 Newton seconds is the net impulse. So now, again, because this is the net force, we can use the fact that change in momentum is the net impulse. So on the right-hand side, I have 250. On the left-hand side, I have 4 v final. Dividing both sides by 4, I get that v final is 125 over 2, so 62.5 meters per second is v final. All right. So I have one last little thing that I wanted to talk about, which is this. You guys have your second midterm coming up. It's going to be the week after Thanksgiving vacation. And so I did want to talk about a little caution. Okay? Students are often confused by work and impulse and the difference between the two. So work and impulse. So I want to talk about the difference between work and impulse. Work was the area under the curve of a force versus position graph. So this area under the curve was work. Impulse is slightly different though. Impulse is the area under the curve of a force time graph. So this is one of those situations where if you do not read the axes, if you do not notice that, force position versus force time, you will get the wrong answer. So you got to be careful here. All right? Make sure you pay attention to those horizontal axes. Now, what does work do? Well, work is the change in energy of the object, because work is energy transferred into a system. All right? Impulse, on the other hand, is momentum added to the system. So you can see how they're closely related, but they're not the same thing. So work is to energy what impulse is to momentum. Okay? So you're going to have a problem. You're going to have two problems on the midterm where one is a force position graph and one is a force time graph, and I just don't want you to be confused. Okay? So that was my caution. And that is my lesson for today, so I will see you